Hello together. In our last video we defined the operator norm for any bounded linear transformation between two normed linear spaces. Now here up front I want to derive one corollary for the operator norm of the composition of two bounded linear transformations. So suppose you have three normed linear spaces x, y, and z, and you got two bounded linear transformations, one from x to y, that's we call S, and the other one t from y to z. Then you can look at the composition, very much like in real analysis you can look at the composition of two functions. So if you think about this, the composition in this order, so S first and then t last, this will be a map from x to z. Now the claim is here, this is actually a bounded linear transformation from x to z, and I have this cute little inequality for the operator norm of the composition. Okay, this is what one usually calls submultiplicative. So in other words, the operator norm of the composition or the product of T and S is not just the product of the individual operator norms, but it is an upper bound. Okay, so let's prove it. Well, first off, a few things. By linearity, I have to check that the composition is actually in here. Let's do this quickly. So by linearity of t comma s, we have for any x, y, let's see, in x, and alpha, beta in f, that so t of s of alpha x plus beta y. Well, in the first instance you're just going to use the linearity of s. You're not going to touch the action of t outside, so you have alpha sx plus beta sy, and now in the second instance you use the linearity of t outside, right? So you're going to get this is equal to alpha t of s of x plus beta t s of y. Okay, and that is the linearity. It is linearity of ts from x to z is established. We need to show that the composition is also bounded, but that is easy because we used the very first theorem of this class. The boundedness for a linear map on normed linear spaces is equivalent to continuity, and since both of these two t and s are continuous because they're bounded linear, their composition is again continuous. This is result from metric space modules, say. Okay, so also compositions of continuous functions are continuous. So together we have that the composition Ts is bounded linear from x to z. Okay, so now it remains to just verify the inequality. But there again we use the same strategy that I mentioned in the last video. First, do not concern yourself with the suprema, just work for any x, tsx in z. Now here composition of function is associative, so you can put the brackets in here as you want. And now I use the usual trick that I have now used already twice. Let me write this here. For a general linear transformation Tx, you always have this inequality for all x in x. Okay, and that's what you use here. So here in the first instance this would be your sort of x tilde. So this is less than or equal to the operator norm of t, and then the norm of the x tilde, which is s of x, and that is actually a norm in y. And then you use the yellow thing again, now with t being replaced by s. So you have that this is equal to t times s times x, and this is now an x space. Since this holds for any x, right now I didn't divide by anything. So in turn, if you look at the supremum over non-zero x of the ratio tsx z over x, well, then you use what you have up here, that this is at most equal to this. If you divide out this ratio, what remains is precisely the product of the individual operator norms. Since it's less than or equal, then the supremum will also be less than or equal to that product. Okay, and that's it, because this here is precisely the operator norm of the composition. Okay, that's it. End of proof. Good. Now, moving ahead, let's discuss some examples of bounded linear transformations, and let's compute operator norms, or at least estimate them. The exact computation of operator norms, this is in general a very hard challenge. Sometimes possible, sometimes no one knows how to do it. So let's look at some easy examples up front. This first example now, it will explain why in linear algebra you only talk about linear transformations or linear operators and you never use the word bounded there. Okay? So let x and y with their respective norms be two normed linear spaces where, or say with, one of them, namely the x space, finite dimensional. Okay, that's a typical setup in linear algebra. Actually, in linear algebra also the y space is finite dimensional, but here it's enough. Then the claim is then any linear map T from x to y is a bounded linear transformation. And that's why in linear algebra you never use the word bounded, because everything automatically is bounded. You don't need to give any further emphasis on that concept. Okay, let's show it. Indeed, as usual, finite dimensions, you work with a basis. So if xi is a basis, then for any x you expand it in the basis with coordinates xi, so the alphas are the coordinates. Then for any x we have, so now I have to estimate t of x in y, and actually this estimation is completely similar to the first estimate that we used when we proved the equivalent norm theorem in the second and third lecture. So I have j1n alpha j. Okay, I switched my indices from I to j, that's okay. Oh yeah, I'm missing something. So this would be x, but now t acts on it, and since t is linear you can pull out the scalars and the summation. So you have this is in y. Now you use the triangle inequality, the sum comes out. Then you would have the norm of alpha j times txj. Well, norms are homogeneous, you can pull out the scalars, and then you have this. This is extremely similar to what we did at the beginning of the proof of the equivalent norm theorem. And now what you do is you can either sort of optimize over this. This will give you a c if you take the largest and then you use Cauchy-Schwarz, or you can use Cauchy-Schwarz right now. So this is really your choice. Let's do it right now for a change by Cauchy-Schwarz in Rn, because here I'm just summing over real numbers. This is less than or equal to alpha j squared, j from 1 to n, square root, and then the same thing, j1n, txj, y squared, and square root. Okay. This here up front, this is what we called in the proof of the equivalent norm theorem the Euclidean norm of the coordinate vector alpha. So alpha is just say a row vector of the coordinates alpha 1 up to alpha n, and this will be your constant, which is finite, because you take a sum of finitely many quantities, each one of them being finite. So you have this, all right? Then now use because right now you're not done yet, right? You have estimated t of xy in terms of the Euclidean norm, not in terms of the norm on x. Yeah, but x is a finite dimensional vector space. The equivalent norm theorem tells me that any norms on that finite dimensional space are equivalent to one another. So in particular, the Euclidean norm will be equivalent to the x norm on the space x. So now use that knowledge, use the equivalent norm theorem and conclude txy less than or equal, say, some constant d and then norm of x. Okay, that's it. And d is positive, say. And this holds for all x in x. And this shows that indeed any linear map that starts on a finite dimensional vector space is a bounded linear transformation. This shows T and L, X, Y. Again, also a reason why we're not so much concerned about finite dimensional spaces in this class. Next example, more interesting. Let's work with a sequence space. So we defined there was a vector space of continuous functions that we equipped with some norm from 0 to 1, and then there was sequence spaces. Let's work in a sequence space, and then later there will be example with the continuous functions. So let Tn be a bounded sequence. This was L infinity. Define a map from LP to LP for P ranging from 1 to infinity as the, well, we can give it a name, multiplication operator. This guy we will encounter later on in the class again. So what it does is the following. It takes T, let's quickly go back here. This is page 21, I think, yep. Yeah, page 21. So what does the thing do? Well, it multiplies by the sequence T, that's why multiplication operator. So it maps the given sequence to the following one. It multiplies each entry of the sequence with the corresponding entry in the T sequence. Like this. Okay. Then, a few things to be checked, clearly. T is linear, because how you add sequences, you add them component-wise. That's clear. So T is linear on LP N with the P norms. Now we have to check that it is bounded. Okay, so let's do this first for P away from infinity. Let me remind you what are the P norms, and I usually raise them to the power P because they don't have to carry around the roots. So this is Tn, x, and p, because the jth term up here is tj, xj. That's why here it's Tn, x, and then a sum over the ends. So what you do this, now you estimate very much as usual. You split up that modulus in the middle. You optimize the first factor. So this is less than or equal n from 1 infinity. You take the supremum over all, let's call him m to not confuse ourselves. You have this, supremum ends here, and then you go out with xn to the power p. And this supremum is finite because it is precisely equal to the infinity norm of t raised to the power p, right? So a little thought reveals that this supremum of tm to the power p is the same as the pth power of the supremum of tm. In other words, you can move that p power outside, all right? So what you have here now is this is equal to the infinity norm of p raised to the power p, and then n1 infinity x and p. So if you take now the pth root, you have txp less than or equal to t infinity and the p norm of x. This was for p away from infinity. For p equals infinity is actually easier. You have t of x infinity, which is the supremum over all n, say, of tn xn. And now you do the same trick as up here. You split here, you optimize the first factor over all n, you keep the second one as is. What comes out is precisely t infinity times x infinity. Okay, all together. T is a bounded linear transformation on LP n with, we have an estimate for the operator norm. So look here, we have this quantity here and this quantity here. If you divide by x here and there, and then you optimize over all non-zero vectors, it will tell you that the operator norm cannot exceed the infinity norm of small t. That's the sequence I started with. All right, now that is an estimate. Usually getting those estimates is easy. At least it's easier than actually now figuring out whether this is an actual equality or if the operator norm is strictly less than the infinity norm of t. Here we can actually show that it's equal to it. As it turns out, we have t is equal to the infinity norm. Okay, let me put this in red. We will use this later on in the class again. So the operator norm of the multiplication operator on small lp is the infinity norm of the sequence that you multiply with. So how can you show this? Well, sometimes you can get lucky and you can find a sequence where you have equality here, right? So here what we always did is we estimated. We estimated here and estimated there, but maybe I can construct one sequence where equality is achieved, and then automatically I know that this here is an equality. Now, but this is in general hard. Now what we will do is we will show we can get arbitrarily close to this upper bound here, and that will be enough. All right, let's do this. As it turns out, we have to show this. Let epsilon positive be arbitrary. Then, by definition of the supremum, there exists capital N, which depends on epsilon, so that T capital N exceeds that supremum once I subtract the quantity epsilon. That's a typical thing. A supremum is a least upper bound. So if you take some small quantity away from it, automatically you can find some term that will exceed supremum minus that small quantity. That's what we do here. Now consider, we define a sequence. Now consider sequence y, y1, y2, y3, so on and so forth. And what are the terms? Well, yn is equal to 1 if small n is equal to capital N. Remember, this was the quantity that depends on epsilon. And otherwise, we'd set it equal to 0 if n different from n epsilon. Okay. So in other words, this is a sequence where only one term has a non-zero entry. Then, that being said, what are the p-norms of that sequence? Well, if there's only one term that is 1 and all the other ones are equal to 0, if you either stick it into the sums or into the supremum, you will get that this has equal 1 norm. And what can I say about TYP? So remember what T does. It multiplies here each entry with T1, that one with T2, that one with T3, so on and so forth. Yeah, but only one of those is actually contributing to the whole part, and that's the one where small n is equal to capital N. You can convince yourself that this is precisely T capital N in complex modulus, because that's the only one that contributes. That's when small n is equal to capital N and T multiplies that entry precisely by small t sub capital N. Okay, and by choice, this is T infinity minus epsilon. Good. Thus, now comes the punchline. The operator norm, which is a supremum, I can take the supremum over the sphere, xx equal to 1. Here actually these are p-norms, so I can be more precise than this. xp is equal to 1, t of x. Now here I have found one element that is on the sphere, so that supremum is going to be at least as big as this element. And here's a p, typ, but I know from here that this is at least t infinity minus epsilon. So what you have is operator norm of t gets arbitrarily close to the infinity norm of small t, because epsilon was arbitrary, hence which shows the reversed inequality, so that operator norm of t is at least the infinity norm of small t. You combine it with the previous part, you get equality. Okay, so this worked out nicely. Good. I want to do one more example about the sequences. I think I will do the example about the continuous functions in the next video. So again, consider LPN with the P norm and the following two operators. So R, this is super easy, LPN, this is the right shift. What does it do? Well, it shifts a sequence 1 unit to the right. That's why right shift. So if you have x1, x2, what it does is it inserts a 0 here and then starts the whole train 1 spot to the right. Okay, that's the only thing it does. There's nothing much to be shown here. Clearly, I will say Rxp is equal to xp for all x in x, because if the p is away from infinity, you're looking at sums. Yeah, but if you insert 1 0 into the sum, you're not going to alter the result at all. And same for the supremum. If you insert 1 0 there, you're not going to alter the result. So what it gives you right away is that the operator norm is equal to 1. So clearly R is a bounded linear transformation on little lp, and the operator norm is actually equal to 1. Last example for this video is not right shift, but left shift. So L, let me see how I wrote it here for R. Okay, so we have L is LPN to LPN, what does it do is it moves the whole train 1 unit to the left. But that means in turn it will chop off the information in the first entry. So now it doesn't start here with x1, it starts with x2, x3, x4. So that thing annihilates some information. Nevertheless, you can convince yourselves easily. I'll write it down. If you look at LXP, now of course it's not going to be equal to the p norm of x because you're missing the first entry here on the right. Yeah, but then you add it artificially to it, so surely Lx of p is at most equal to the p norm of x. But if you look at this sequence, so there's one non-zero entry. In the second entry, everything else is equal to 0. This guy is mapped to 1, 0, like this. And under this special example, you actually have equality up there, right? So this means in turn that the operator norm of the left shift is also equal to 1. Okay. Also, the left shift, therefore, a bounded linear transformation. Linearity is clear because you add those sequences by adding their entries component-wise, and that here shows already that it is bounded linear. And now we can actually do better. Here's one example where you have the equality, so the operator norm is equal to 1, because through this one here you just get that it is at most 1, but for this example you achieve equality. Okay. I think I will stop here. At the beginning of the next video I will have one more example. This is about continuous functions, and then actually we are done with this first chapter on normed linear spaces and we will move to Hilbert spaces. Okay, see you next time.